There you go.
It's a pleasure to have here today Professor Ricardo Doretto from UNCAMP. Ricardo did his undergrad and his PhD at UNCAMP, same place as I did. He went for 2 postdocs in Holland, in Utrecht, with a former student from UNCAMP too, Christiane Moraes-Smith, and then to Cologne with Matthias Reuter, a renowned physicist in Germany. And then he has been back to, he went for some time at in São Paulo, and then he was hired at UNCAMP in 2012 and has been since. Today he's going to talk to us about mean field theory of interacting triplons in a 2-dimensional valence-bond solid, stability and properties of many-triplon states. So thank you very much for accepting our invitation, and the microphone is yours.
So thank you, George, for the invitation, and it's a pleasure to be here today to tell you a little bit about our recent results concerning valence-bond solid, in particular many-triplon states. So triplons are nothing else but the elementary excitations of a valence-bond solid. When a valence-bond solid sets in, some lattice symmetries are broken, for instance, some translational symmetry. One question that we asked was, could the many-triplon states restore some of the lattice symmetries that are broken when a VBS sets in? In case the answer is yes, we ask a second question. Could a many-triplon state describe a spin liquid phase? If the answer to both questions were yes, we could provide an alternative way to study spin liquid phases. Usually, spin liquids are studied using the so-called Schwinger boson formalism. Valence-bond solid phases are studied using the so-called bond operator formalism. If the answer of those 2 questions were yes, we would have an alternative way to study, to describe the spin liquid space. In order to answer those 2 questions, we choose a particular model, the J1, J2 Heisenberg model on the square lattice. And unfortunately, for this particular problem, the answer is no. But in the way trying to answer this question, we study many-triplon states and we try to determine some properties of these kind of states. If you don't have any idea of what is written in this slide, don't worry. I will try to explain all the concepts in the following. Okay? So please don't go away. And if you want to know a little bit more, please take a look in this PRB paper. This is the structure of the talk. I will start saying a few words about the
Sorry.
Wait.
There is a small window at the bottom of your slide. Can this be removed?
I think it will disappear, but let me try.
Okay, so it
disappeared.
It has to stay there, right? Okay.
Yes. I'm so sorry.
Sorry for that.
Okay, I'll go back. Okay. Is the slide back?
Yes.
Okay. As I said, this is the structure of the talk. I will start with saying a few words about the J1, J2 model on the square lattice, introduce and give a few words also about the valence-bond solid and spin liquid phase. Then I will introduce the formalism that we use to study valence-bond solids, the bond operator formalism, show some results that we derived for the J1, J2 model, assuming that the ground state is a columnar VBS at this harmonic approximation. It's a kind of mean field approximation that we use to describe valence-bond solid. And in the second part, I will move and say a few words about many-triplon states, in particular, the results that we derived using a mean-field approach. I will show you the excitation spectrum and some spin-spin and dimer-dimer correlation functions. We also calculate bipartite entanglement entropy, but unfortunately, due to time constraint, I will not be able to show you these results, but we can discuss later, no problem. Okay, so let's start with the Heisenberg model, the J1, J2 model. It's nothing else but a Heisenberg model where we consider both interactions between the first and the second neighbors. Both couplings are positive, both couplings are antiferromagnetic. The classical phase diagram, when the spins sitting at the lattice sides are larger, the classical phase diagram is null, and what we have the following. For instance, when we are here with a small J2, the ground state looks like this. If it has long-range magnetic order, it has Néel order. Note that the spin's first neighbors, they point in the opposite direction. The J1, J2 model on the square lattice, it's a nice example of a first-rate magnetic system. The reason is that in a first-rate system, we are not able to satisfy all pairs of interactions. Note that here we have antiferromagnetic interactions between first and second neighbors. So both first and second neighbors want to be in the opposite direction. Both spins want to point in the opposite direction. But note that for the Néel phase, only the first neighbors are happy. The second neighbors are unhappy. They are frustrated. So that's why the J1, J2 model is an example of a first-rate magnetic system. If we now go to J2 of order of J1, we also have ordered phase, in this case a collinear phase, where now the spins along the diagonals here point in opposite direction, and for instance, in this particular picture, the spins along the y direction, they point in the same direction, same direction. The phase transition between those two ordered phases takes place at J2 equals 1/2. Let's now move to the quantum case. Let's now assume that we have spins 1/2 sitting at the sides of our square lattice. The phase diagram is known. What we know is that between those two regions with magnetic long-range order, there is one region here, which is called disordered region, where what is known is that the ground state does not have long-range order. But the nature of the ground state here is not known. There are some proposals. For instance, when we are in this region here, for instance, around J2 equals 1/2, the spins don't know what to do. But they know that due to this kind of antiferromagnetic interaction, they can decrease their energy if they combine into singlet states. So what I show here with these blue ellipses is that this spin and that one, they are in the singlet state. Of course, this is going to happen for all pairs of spins near lattice, and we could have, for instance, something like this. Ordered distribution of singlets in the lattice. This is the valence-bond solid. This picture that I'm showing you here in particular is a valence-bond solid, a VBS. I will use this term in the following, a VBS with columnar order. So this is one proposal for the ground state of the Néel for the J1, J2 model in the disordered phase. In addition to this particular case, the columnar arrangement, we could have something also like this, where now our singlets, they are in the staggered distribution. And we could even have something more exotic. For instance, we could take 4 spins on a given placket. These 4 spins could combine in a singlet state. And we have here a placket, and then we have regular distribution of plaquettes along the lattice. This is what we call a plaquette VBS. Okay. In principle, all those states are good candidates for the ground state here, but at the moment it's not clear which one is the possible ground state. Okay, so valence-bond solids are what we call quantum paramagnetic phases. And when you think about VBS, you should basically think about a crystal of singlets, like the columnar one that I show here. Note that there is some long-range order, but the magnetic order is restricted to one lattice space. That's what I put here. Since the ground state of a VBS is a product of singlets, so the ground state preserves spin rotation symmetry, but note that some lattice symmetries are broken. In the case of the columnar VBS, we break both translation and rotational lattice symmetry. In the case of the plaquette, only translation symmetries are broken. What about the excitations? They are simple. Yeah? We basically break one singlet and turn it into a triplet. These kind of excitations in general are gapped because we pay energy to break the singlet, and they are called the triplons. A VBS also is an example of what we call a confined phase. Why? It's also simple to understand. Suppose that we break the singlet, create one triplet, and now started to move one spin away from the other. For instance, as I did here, I take the spin from this side and put the spin here. When we do such kind of move, note that you have to change the singlet arrangement between the two spins. And if you do so, you increase the energy of the system because this arrangement is not part of the ground state. So this guy cannot go further away. It has to go until some, let's say, fixed distance. And in other words, this guy and that guy, they are bound, they are confined. So VBS is an example of a quantum paramagnetic phase. Another example, which also is another candidate for the ground state of the J1 and J2 model in the disordered region, are spin liquids. And when you think about the spin liquids, you could think about a liquid of singlets. The picture here is a little bit more complicated than in the case of the VBS, but we can think that way. Suppose that this is the wave function of your spin liquid ground state, and it's made out of different spin coverings of your lattice. For instance, this is one component of your ground state of your wave function. This is a second component, and you have more. Okay? So the picture here is a little bit more complicated than in the VBS, but we can still think about this liquid of singlets. Again, spin rotation seams is preserved also as in the VBS, but now both translational and rotational lattice symmetries are also preserved. So it's different from the VBS. What's also different from the VBS that we can here have both gapped or gapless excitation, depending on the kind of spin liquid ground state that you have. Excitations in this case are given by spinels, not by triplons, as in the VBS case. And it's also easier to understand why this is the case. Let's do the same exercise that we did for the VBS. For instance, I go here, I break the singlet, I turn it into a triplet, and then I take the spin from this side and put it here, as I did here. Again, we have to modify the singlet arrangement between the two spins. But here we don't pay anything because this arrangement is also part of the ground state. So we can even take this guy and take it away and stay only with this only with this spin or this spinel here. Okay? So this guy is the elementary excitation of a spin liquid. Since now we can break, or we can break this bound state, a spin liquid is also called a deconfined phase. VBS is a confined phase, while a spin liquid is a deconfined one. One spinel is also said to be a fractionalized excitation. And it's also easy to understand why we can always spin a fractionalized excitation. Recall that in general, we can label our elementary excitations, or we can put our elementary excitation in two groups, either particle or collective excitations. For instance, in a Fermi liquid, in a metal, the elementary excitation are quasi-particles, and we know that they are characterized by the quantum numbers spin 1/2 and charge plus minus e. In an ordered state, either a ferromagnet or an antiferromagnet, elementary excitations are collective ones, for instance, spin waves, or in a VBS, they are triplons. In this case, we have excitations with spin 1 and no charge. Note that a spinel has both characters. It has spin 1, but has no charge. So in principle, we could put the spinel here, but also we could put the spinel here, but no, it has no charge. So it's not possible to fit the spinel neither here nor here. Since they do not have all the quantum numbers which characterize either a particle or a quasi-particle, we said that a spinel is a fractionalized excitation. It's somehow similar to the fractal quantum Hall effect, where the elementary excitation has charge E over, for instance, E over 3 in the case of the fractal quantum Hall system at a filling factor 1/3. It's more or less the same idea. Okay, back to the J1, J2 model. I show here all the proposals for the ground state of the system in the disordered region. So in addition to columnar, stagger, or placket valence-bond solid, there are also some proposals of a mixed VBS with both columnar and placket character. Are also proposals which include gapped or gapless spin liquids. And more recently, people are talking about the spin liquid and VBS phase. To explain this a little bit better, let me show you this very recent result determined with machine learning. And it agrees with also some DMRG results also from last year. And what they found is the following. So this is the disorder region from 0.4 to 0.6. What they claim is that for J2 somehow below 0.5, below 1/2, a spin liquid phase may set in, while for J2 larger, a VBS phase may be the ground state. In particular, they talk about columnar VBS. I didn't write all the reference here, but in case you are interested, you can just go to the introduction of those two papers, and all the corresponding reference will be there. Okay. One point that I should mention is that I'm not interested in determining the ground state of the J1, J2 model. I'm just interested in the fact that what matters to me is that a columnar VBS is a possible state that are stable in this region. It doesn't matter if it is the lowest energy one or not. I'm not trying to answer this question in this talk. Okay, that's something important to clarify. Okay, so that's the brief introduction about the system that we choose to study many-triplon states. Let me now tell you a little bit about the formalism that we use to describe valence-bond solids, and also that I'm going to use to study many-triplon states. So the formalism that we use is the so-called bond operator representation, which was introduced in the 90s by Sachdev and Bat, and it's very easy to explain what the ideas behind this representation if we look at two isolated spins 1/2. As we know, the Hilbert space of the two spins 1/2 has dimension 4. The basis that we use now is made out of 1 singlet and 3 triplet states, as for instance, right here. Let's assume the following. let's assume that we introduce S and 3 P operators, a singlet and 3 triplet operators, boson operators, that with the following property. When I apply S or T in a fictitious vacuum, what I do is to create the corresponding singlet or triplet state. Okay? So we introduce one singlet operator and 3 triplet operators. Now we do the following. We look at the 6 operators that we have here. So we have X, the component X, Y, and Z of the spin 1 and the spin 2. In this Hilbert space of 4 dimensions, we can calculate all the matrices which represents the 6 operators. And then we realize the following. If you expand your operators, your spin operators, component X, Y, and Z, in terms of singlets and triplets as shown here, this representation combined with this property exactly reproduce the matrices that we calculated before. So this is indeed a very good expansion of your spin operators in terms of boson operators. It somehow recalls you the Holstein-Primakov representation, but Holstein-Primakov is suitable for ordered phase. Here, I'm not disordered phase, in a valence-bond solid phase, so that's why we choose bond operator representation. Of course, when we write spins in terms of bosons, we should take some care because we introduce at that point some unphysical states. We have to remove them, we have to take care, and we do so by introducing this constraint in the theory. I introduced the representation for 2 isolated spins, but it's easy to generalize it to a lattice, to spins on a lattice. Basically, we have to add here one lattice index, and then with this, we can describe a VBS. So that's the idea. We now will focus on the J1, J2 model. We particularly choose the columnar VBS as our reference state, and now we will describe this phase using the bond operator representation that I just introduced. Okay? Well, the first step is to map your spin problem into a bosonic problem, a problem in terms of bosons. To do this, I have to identify which spin is the spin 1 and which spin is the spin 2. We did this by working not with the original square lattice, as in this case, but we work with the lattice, the underlying lattice defined by the singlets. For this particular case, for this particular arrangement, for the columnar arrangement, you note that the underlying lattice is a rectangular lattice. So this is, for instance, this is side 1 of my lattice, and this is the spin 1, and this is the spin 2. That's what I draw open and full cycles to identify spin 1 and spin 2 in all my previous pictures. Once we identify the underlying lattice defined by the singlets, we now have to rewrite the original spin Hamiltonian in terms of the Hamiltonian written in terms of spin 1 and spin 2. For instance, the interaction between those two guys here are given by this term, saying side I, spin 1 and spin 2. The interaction between those two guys here are given by this term, interaction between spin 1 and spin 1, side I plus tau 2, etc. Once you have your spin model in terms of spin 1 and spin 2, now the mapping from the spin model to the boson model in terms of singlets and triplets are exactly. There is no approximation at this point, only the fact that we choose a particular underlying dimerized lattice. Before I show you the effective bosonic model, let me just say a few words to understand the structure. Recall that within bond operators, all spin singlets are quadratic in boson operators. The original Hamiltonian is quadratic in spin, so when we do the mapping, we end up with a quartic Hamiltonian in terms of bosons. If we look closely to all terms, we can identify terms with no spin, no triplet operators, 2, 3, and 4 triplet T operators. As I said, we have to introduce a constraint, so we have to add here a Lagrangian multiplier. Here I was not so careful. In fact, this mu should be here, and it has to depend on the lattice site. But since in the following I'm going to do a mean field approach, I already put it outside and wrote it independent of the lattice index. Okay, but we have to include such a constraint to make sure that unphysical states are removed from our problem. I have also to make sure that I'm in the columnar VBS phase, and how we proceed here, how we do this with the bond operators. Basically, we assume that the singlets, they condense. So this Hamiltonian here is written in terms of SI and TI alpha operators. I will do the following. Every time that I found a singlet operator, I will replace it by its corresponding expectation value in the ground state, which is not else but the square root of the number of singlets at site I of the dimerized lattice. This is somehow similar to what is done when you study BEC in the so-called Bogolo-Bond approximation. You do the same kind of replacement when you describe a BEC in the Bogolo-Bond approximation. But the point is, once we do this, we end up with a bosonic model now only in terms of the triplet T operators. We remove the singlets from our description. Okay? So this is an approximation. This is not an approximation, this is exactly mapping, but at that point we indeed do an approximation. And that's the way the effective boson model looks like. So H0 does not include any triplet operators. H2 is quadratic, H3 is cubic, and finally H4 is quartic. Now, how do we treat this interacting boson model? We do the simplest thing that we can do. Basically, we neglect H3 and H4 and approximate our problem by those two guys here, because now we have a quadratic problem that we can diagonalize and try to understand a little bit the features of the system. And that's what we do. This is the so-called harmonic approximation, which in this context is a kind of mean field approximation, because we just neglect H3 and H4. We know that this quadratic Hamiltonian we can diagonalize, for instance, via a canonical Bogolo-Bond approximation. And when you do so, you introduce new bosons, which I'm here call bosons B. Note, the operators 3 I'm calling the triplet operators. The new ones will be the elementary excitation of our VBS. The B operators are indeed our triplets. Now, it's easy to show that the Hamiltonian after the Bogolo transformation is quadratic, assuming this form, and that the energy of the triplons are nothing else but the square root of those of A squared minus B squared. So we know everything. There is something missing at that point. I don't know if you can see here, but because it is hiding, but anyway. At that point, we determine the energy of the triplons for fixed J2, but recall that we don't know at that point yet the Lagrangian multiplier U and the parameter N0. But we can easily calculate those two guys, simply taking these saddle pointing conditions, and these two saddle pointing conditions will give us two self-consistent equations that we numerically solve and determine mu and N0. So we fix J2 and solve those two equations, calculate mu and N0, and then we have the ground state energy and the excitation spectrum of our triplets. And that's what we found. So when we try to solve our self-consistent equations, we see that we find solutions only for J2 from 0.3 to 0.63. If you recall the phase diagram of the model, you may remember that the disordered phase goes from 0.4 to 0.6. So it's more or less okay. We might recall that we are doing some mean-field approximation. So the limits of the disordered region is somehow overestimated at this mean-field level, but still it's more or less in agreement with previous results. Note that here I show you N0, the red line, and also the parameter mu, the green line, as a function of J2. And note that N0 is not equal to 1, but it's a big number. No? It's around 0.85. This means that this picture is not the completed picture to understand a VBS. It's more or less one first approximation. No? But since N0 is a little bit smaller than 1, it means that some of your singlets here are turned into triplets. There are a finite number of triplets T in your ground state. Okay? What about the excitations? What's nice about the bond operator formalism is that you have access to the excitation spectrum above your ground state. Here I show you the excitation spectrum when we fix J2 equal 0.48 along the lines in the dimerized Brillouin zone. The original Brillouin zone associated with the square lattice is this dash square I'm showing here. But we are working within the dimerized lattice. So that's why the Brillouin zone is a rectangular and not a square. What are the features of the spectrum? It's gapped, as I announced at the beginning. No? A VBS is characterized by a gapped ground state. And in particular for J2 equal 0.48, the gap is here in the Y point. If I now increase a little bit J2, for instance, 0.52, we still observe a gapped excitation spectrum, but notice that now the gap is at the gamma point at the center of the first Brillouin zone. Of course, you can do this for all values of J2 in this range from 0.3 to 0.63. And if you do so, you have the gap. The gap is of your VBS phase as a function of J2. What notes that when we increase J2, when we are exactly at J2 equals 1/2, the position of the gap changes from the Y point for J2 smaller than 1/2 to the gamma point for J2 larger than 1/2. And another point, at the transition, when we start to find solutions for our self-consistent problem, note that the gap is still open, and this is somehow related to the approximation that we are using, this mean-field approximation that we are considering. Okay, suppose you want to go beyond the harmonic approximation. You can do this. I didn't do this in this talk. I'm not going to do this in this talk, but we did this before in this paper here, which is a study for VBS phase in the dimerized Heisenberg model on the triangular lattice. And in that case, we treat both the quartic and the cubic term, the quartic term at the Rutherford approximation and the cubic term in lowest order perturbation theory. If you do so, you can calculate corrections to your harmonic spectrum. Basically, for this particular problem, we show that when you add H4 and H3, the energy of your excitation spectrum decreases. Due to the fact that the triplet, the cubic interaction or the cubic vertex has this form, the lowest order diagrams for your self-energy are bubble diagrams like this. Okay, so in principle, you can go beyond the harmonic approximation and correct some and correct the harmonic results. Okay. We also did this for the J1, the J2 model, but in a different context. We followed this procedure from previous slides, but we did this for the placket VBS. Of course, in this case, I cannot use the bond operator representation that I described before, because the one that I described before is suitable for dimerized phase. Here, we have a tetramerized phase. Recall that if you have 4 spins 1/2, the Hilbert space has dimension 16. It's made out by 2 singlets, three families of triplets, and 1 quintet. So you have to generalize this bond operator representation to properly describe the placket VBS. So if you want, I can comment more on that result later. But in case you are interested, please just take a look at this paper here. Okay, so let's now go back and indeed start to look at the many-triplon states. At the beginning, I told you that the idea to look at the many-triplon state is somehow related to the fact that maybe a many-triplon state could describe a spin-liquid phase. And let me now try to explain in more details what we have in mind when we thought about that. As I said, a columnar VBS, for instance, it breaks some lattice symmetries when the ground state sets in. Suppose we start with the columnar VBS and we excite a lot of triples. So we break a lot of those singlets and turn it into triplets, into triples. Recall that those guys, they interact. We call the H3 and H4 term. So after exciting all those guys, they could interact and they could return to a state with a singlet arrangement, but maybe the arrangement is not equal to the original one. It might be different. It could be something like this. It could even have some longer singlets. And it could even be not only one unique singlet cover, but it could be a linear combination of those curves. If it were the case, we would have a spin-liquid. In principle, we would have a spin-liquid phase. Okay, so that's the kind of idea that we had in mind, which lead us to study many-triplon states. As I said, for this particular system, the answer is no. But in the meantime, we are able to characterize many-triplon states. So that's the second part of the talk. That's what I'm trying to tell you in the fall. Okay, we want to study a system of any triplons, the B operators. I try to make the difference between the original T operators and the B operators, which are indeed the triplons. Recall, after the first mapping, when we went from the spin Hamiltonian to the bosonic Hamiltonian using the bond operator representation, we end up with a Hamiltonian in terms of triplet T operators. When we did our study at the harmonic approximation, we properly well-defined a relation between the triplets T and the triplons B. So we have a well-defined relation between T and B, and we can use this here and map now, do a second mapping to a Hamiltonian only in terms of triplons B. That's what we did. So H0 and H2, we already know. It's nothing else but our harmonic Hamiltonian. The cubic term goes into a cubic term in terms of triplons B. The quartic term goes into a quadratic term in terms of triplons B and a quartic one. In the following, in our mean field approach, we will not include H3, only these three guys here. This new quartic term now, it includes some terms, some operators that do not conserve the total number of bosons. For instance, this guy here has one term which has 4 B-Daga terms. So when we do our mean field analysis of this new Hamiltonian, we have to consider both normal and anomalous expectation values. Okay? And of course, we have to introduce a Lagrange multiplier to make sure that we can control the number of triplons, which I'm here called any bar, in our system. Okay? So that's the way the theory looks like after you do all your mean field analysis, all your mean field approximation in this new quartic Hamiltonian in terms of B values. It looks like our previous harmonic Hamiltonian, but now, of course, we have different A and B prefactors or functions that I call A bar and B bar. The harmonic result is here in this omega. Again, we solve this problem via Bogolubov transformation. We introduce new bosons, now the A's, which are excitations above the many-triplon ground state. We can diagonalize it and calculate the energy of our new excitation, our A's. And it's a little bit it's on top, but the problem there is one self-consistent problem still to be solved. Recall that we have to determine the normal and the anomalous expectation value. Those guys are indeed in this delta 1 and delta 2 function here. So what we did was the following. Based on the harmonic results, now we fix J2 and we fix any bar the number of triplons, and we solve the self-consistent problem. Okay, that's basically what we have to do at this point. And once you do this, you have both the energy of your many-triplon ground state and the energy of the elementary excitations above your many-triplon ground state. Before showing you the results, let me just comment something important. It's easy, it's possible to show that the ground state of this Hamiltonian, assuming this form, which is nothing else but a kind of BCS-like wave function. So at the beginning, we could think that since we know now BCS wave function correlates triplons with momentum minus k and k, we could think that a many-triplon ground state is nothing else but a triplon pair condensate. But this is not the case. It's not the case because our original Hamiltonian in terms of the beats do not conserve the U1 symmetry. There is no U1 symmetry broken in this case, so we cannot say that a many-triplon state is indeed a triplon pair condensate. Okay, just one point to be mentioned. Okay, let me now show the results that we found when we studied this many-triplon ground state. As I said, we solved our self-consistent equations for a fixed J2 and for a fixed any bar, a system with a fixed number of triplons. And what we realized is that for configurations below this green line here, our self-consistent equations converge and we have solutions. So for all configurations below the green line, we have solutions of our self-consistent problem. Here, we didn't find any solution. You can see this picture here as a kind of phase diagram. Okay, so below the green line, we have many triplon ground states. Here, we don't. Now, if you look closer to the solution, we realize the following. For configurations in this region here, above this red line and below the green one, there are some configurations where the number of triplets, the original triplets T, is larger than 1. And this is not good. This guy should be at most 1. So we introduced this second criterion, and then we said that we have solutions for our many-triplon system only for configurations below this red line here. Only for this configuration here, we can have solution, but if you move here, no, those solutions are not possible. Okay? So as I said, there's some region, depends on the value of J2, you can find solutions of our mean field equations with a fixed number of triplets. Now, let's look at the ground state energy for fixed J2. For instance, I can choose J2 equal 0.48 and plot, as it's shown in this plot here, I can plot the ground state in terms of the number of triplons in the bar. And what we realize, for instance, look at the solid black curve, which corresponds to J2 equal 0.48. What we realize that the ground state energy is non-monotonic, meaning that there is one state which is the lowest energy many-triplon state. This is corresponding to the blue line here. Okay, so for each J2, we can identify one particular many-triplon state, which is the lowest energy one. And that's one point that you get disappointed, because we are expecting that these lowest energy many-triplon states should be something somewhere like here, with a large number of triplons. But we only find solutions, lowest energy solutions, with a very small number of triplons. This means that this kind of many-triplen state may have properties very close to the corresponding VBS. Recall that the VBS, the columnar VBS, is the reference state. Everything is defined with respect to this columnar VBS. Our triplons are defined with respect to the columnar VBS. Okay. What about the excitation spectrum? Something that we can access with this formalism. Here I show you the excitation spectrum above the many-triplon ground state for J2 equals 0.48 and for the configuration with the lowest energy. So this one with any bar closer to 0.05. I also include the excitation spectrum of the columnar VBS for the same J2, just to give you an idea what's going on. Again, we have a gapped spectrum, and the position of the gap is similar to the VBS. It's also at the Y point. We also look what happened with the excitation spectrum as we increase the number of triplets. What we found is this. So it's qualitatively the same. As we increase the number of triplets, we go from the green line to the blue one. One important point is that the gap still is at the Y point, but the energy of the gap decreases as we increase the number of triplets. We did the same for a larger J2, for 0.52. Again, we find for the lowest energy configuration, lowest energy many-triplen state, also a gapped spectrum, but there is something different compared to the corresponding VBS. For the VBS, the position of the gap is at the gamma point. Now, for the many-triplen state, it is at the end point. It's a little bit different. We also increase the number of triplons to see what's happening with the excitation spectrum. Again, the same qualitatively change. Also, the energy of the gap decreases as we increase the number of triplons, but it's a little bit different from 0.48. For 0.48, the decreasing is a little bit faster than here for 0.52. That's one difference between those two configurations. Note that I choose one configuration for with J2 smaller than 0.5 and one with J2 larger than 0.5. Okay, so in addition to the excitation spectrum, we also calculate other properties of our many-triplen states in terms of the number of triplets. I show you how the excitation spectrum changed as we increase the number of triplets. Now I'm going to show you how the spin and dimer correlation functions behave as we change the number of triplets. We also calculate dimer order parameters and bipartite entanglement entropy, but I'm not going to show you these results here today. Okay, So that's the behavior of the spin-spin correlation function. And here I did two calculations for the spin-spin correlation along the x direction and along the y direction. So these are the results for J2 equal 0.48. What we see is that the spin-spin correlation function decay exponentially. This is somehow related to the fact that we have a gapped triplet system. It's maybe difficult to see, but this dashed line here corresponds to the spin-spin correlation function for the VBS. And the solid black line to the many-triplon state with lowest energy. As I said, they are quite close to what expected. The VBS and the lowest energy many-triplon state may have the same properties. But we see that as we increase the number of triplons, the number of triplons in our ground state, as we go in this direction, the correlation length starts to increase. In particular, when n bar is larger than 0.4, we see that it increases quite fast. Recall that the excitation gap above the many-triplon ground state decreases quite fast as we increase the number of triplons. Now, if you do the same for the correlation function along the y direction, you also see that it increases, it decays exponentially as the one at the x direction, and it also increases as we increase the number of triplets. Note the following. You cannot see here because it's covered, but here's something 3540. For the VBS, the correlation length along the x direction is larger than the one at the y direction. As we started to increase the number of triplons in our many-triplon ground state, both psi x and psi y increase, and if we are in this region for any bar larger than 0.16, they are more or less of the same order. This could be seen as an indication that a many-triplon state, although it's not the lowest energy one, it seems to have a more homogeneous singlet pattern when compared to the corresponding VBS, which has this columnar order. That's what we found for 0.48. Now let's move to 0.52, and there are some different things. Now, if we look at the correlation function along the x direction, we again see something that decays exponentially, but note, there is no modification as we increase the number of triplons. Somehow, the correlation length is the same regardless of the total number of triplons. That's not what we see in the y direction. In the y direction, we see something that increases, the correlation length increases as we increase the number of triplons, but still, it is different from the configuration with J2 equals 0.48. It seems that as we go to J2 equal 0.52, we do not have this more homogeneous singlet pattern. Here, I would like to recall you this machine learning result that I showed at the beginning of my introduction. For J2 smaller than 1/2, it seems to be the ground state is a singlet, or something that has a more homogeneous singlet cover, while for J2 larger than 1/2, the ground state seems to be a columnar VBS. I'm not saying that I'm reproducing these results. What I'm trying to say is that this procedure where we study many-triplet state above a specific columnar VBS seems to indicate what people are seeing in the ground state of the original model. Okay? This is just an indication. I'm not claiming that the many-triplon ground state is describing spinlet. It's just an indication that it seems to go in the right direction. We also calculate the diamond-diamond correlation functions, and we see the same. This is 0.48 and 0.52. Again, for 0.48, there seems to be some kind of a system gets more homogeneous, the singlet cover gets more homogeneous as the number of triplets increase, but not for 0.52. Just to mention some previous work that people have been doing, some previous results that people found when study spin liquids. For instance, there are some Monte Carlo simulations where people take the RVB. RVB is a kind of spin liquid ground state. And they take the RVB wave function and they calculated the corresponding spin-spin correlation function for the square lattice. And what they found is the following. The spin-spin correlation function decay exponentially, as we saw in our case, but the dimer-dimer correlation function has an algebraic decay with this exponent. What's somehow interesting is that now, if they consider the same RVB wave function on the square lattice, but with some larger singlets, not the lowest, the shorter one, which corresponded to two spins, to a singlet for the first neighbors. But if they include longer singlets and also look at the same wave function on the triangular and the carbonyl axis, now they found that both spin-spin and dimer-dimer correlation function decay exponentially. It somehow recalls what we found for the many-triplon state. But again, I cannot say that the many-triplon state is describing spin liquid. Okay, so as I said, we calculate more features of the many-triplon round state as a function of the number of triplets in the bar, and I can comment on that later if you want, but I do not have time to show you. And that's it. Here, I just give you, leave you with my summary. I just want to mention this point here that for this particular study, we choose the square lattice J1, J2 model. As I said, it's not clear what kind of ground state we have in this disorder phase. But for the same model on the triangular lattice, there are more evidence that for J2 in this region, it might be that a gap spin liquid phase sets in. So something that we want to do is to repeat all this procedure now for this model, for this particular model, and see if we get something which may remind us of a spin liquid. For instance, we would like to check if there is a lowest energy many-triplon state, and if this guy now is characterized by a larger number of triplons, not a smaller one as I showed before. And that's it. If you want to see the details, please take a look at our ERB paper. So that's what I want to tell you. Thanks for your attention. And again, thanks, George, for the invitation.
Very, very nice talk.
And so I'm sorry for a little bit, more than 1 hour now. I'm so sorry.
That was in reality 2 minutes before 1 hour.
Okay.
58 minutes. So it was not more than 1 hour. So any questions? Anyone had some? The students. I have a question. I was going to ask you that. Let me turn on.
George, you cannot see you for some reason.
I am turning my camera. Yeah.
Okay, now much better.
I was going to ask you about the RVB. I did long time ago. I did some stuff with RVB. I was going to ask, was the RVB? It's a disorganized, resonating state with. You have singlets, and they can kind of move around. And the VBS seems to be a much more organized thing. So can you comment a little bit on the differences?
RVB is a spin liquid phase, right? When you think about an RVB, you should think about a spin liquid. So RVB, it's a liquid of singlets.
Okay.
And that's the point that the problem is the following. To apply the bond operator representation, we need a reference state. When we study a VBS, it's easy to define. The question, what's the reference state to study a spin liquid phase? So the point is, it seems that, or
it's more or less clear that the bond operator seems to be not suitable to study a VBS, a singlet. That's why we try this procedure of look at many triplon states. Maybe I could come back to this slide here. Okay.
The VBS state is kind of your vacuum, right?
Exactly. Let me show here. When you are in the VBS phase and you want to apply the bond operator representation, it's easy because now we have a very good reference state. No? So this is my site I, spin 1 and spin 2, the map is exactly. But now if I want to study, for instance, this RVB, we do not have this picture. So that's why we thought about that. Maybe if we excite a lot of triplets, of triplons, and then allow them to recombine in a different singlet cover, for instance, like this, maybe we could have a ground state which has a singlet cover different from this one, but not only this one, but it could be a linear combination of different covers. This is more or less the picture of the RVB. No? When you think about the RVB, you should think about this wave function here. This one. Now, RVB is a collection of singlet covers, or as a linear combination of different singlet covers. Our hope at the beginning was maybe a many-triplon ground state could somehow reproduce this behavior. But what we found is no, that this is not really the case.
I understand correctly, you excite the system because every triplon that you create, you are going up in energy.
Yes.
And you let them do whatever they want to do, and then they go back to a lower energy state. Is that right?
That's the picture. I cannot prove you that picture, but this is the picture that's the picture that I have in mind for the many-triplon ground state. But I cannot prove you that that's the case. We expect that even though we create a lot of those singlets, those triplets, they may recombine in new singlets. That's the picture that I have in mind, but I cannot prove that because it's different from here. No? When I'm in the VBS phase, I have complete control of my reference state. Now it's somehow loose. Now I do not have, when I go to the many-triplon ground state, I somehow lose this control. So this is one possible picture, but I'm not in play that this is the picture.
I have another question. If you add doping to the system, if you put mobile electrons there, let's say that you remove, like you do with the cuprates. There is all this that was introduced by Anderson, the idea of the RVB to describe the undoped cuprates, and then when you dope, you would have the superconducting state as already given by the RVBs. Any real life system where you can dope and make this mobile like a TJ1, J2 system or model, let's say?
I know there are some systems which there are some materials that can be described by the J1, J2, but which I'm not completely sure is that the parameters of the material are such that you are in the disordered phase. As far as I know, I'm not completely sure, but as far as I know, the systems that are described by the J1, J2 are always in the ordered phase. So for the particular J1, J2, you cannot realize ground state of this type. But there are some materials in particular materials which are explicitly dimerized, where you can have a kind of DBS ground state. For instance, there is this one-dimensional system, I think it's copper, germanium, oxygen. It's a one-dimensional system. There you can have, there is evidence that you have this kind of spin pairs ground state, and then you could have this RVD ground, this DBS ground state, not RVD.
Okay, okay. I know this spin pair system. Okay.
Yeah.
That one you cannot dope with mobile electrons. I know that you can dope and see what happens with the correlations when you have non-magnetic ions in case of.
Some people, I think I don't remember exactly the reference, but they try to somehow generalize the bond operator representation to include also what you said, that you want to dope, now you want to remove some spins. People did this. There is some work in the literature where there's some, I don't recall the exact results, but I know that it's possible to study, let's say, a doped VBS, if you want, with the bond operators.
And well, I have one last question if nobody else question. Is there anything interesting that you can learn from studying this model in a two-leg ladder system?
In two-leg ladder?
I don't know if, because there you can apply, I am sure you can apply DMRG to very large systems and maybe get a handle on the ground state. But I am not sure if you have any type of order like the VBS in a ladder. I have singlets forming in the runs, or you could have the singlets forming this way. I don't know. It's just a guess.
Can I take advantage of your question and make mine? Sure. Actually, I was thinking about this. This would be some sort of quasi 1D system, right? So have a two legs. I have first and second neighbor interaction only. And as far as I remember, there is a phase essentially within the range of J1, J2, the ratio of J1, J2 you are studying, in which you can see quasi long range order, where the correlation goes like a logarithm of n over r essentially, right? So in your case, my question would be, in your case, do you find some sort of regime like this, especially when maybe you didn't study this situation, as George has asked, when you decrease the size in one direction?
You mean go to a ladder?
Yes, toward the ladder. Yes. The numerical results would be more reliable, I guess.
Of course, yes. The point is, I want to do this in 2D, because in 1D you have the answer. In 1D you can apply the MRG. For instance, for the J1, J2 in the square lattice, you cannot. Now people are trying to do the MRG, but you cannot do quantum Monte Carlo due to this sign problem. And that's why I focus in 2D, because this is a place where you are right in the sense that we could do this 1D and check, because we could compare. Your point is correct. We could do this 1D, and then we could compare better our results with numerical ones, which are absent in 2D. But somehow we decide to stay in 2D because we have this lack of results, and let's see if we can try to do something in 2D and try to. But I agree with you that it would be nicer, to be interested to do in 1D, and because we could compare with numerical results. I agree with you. But I didn't. At the moment, I didn't. I just the only thing that we did was for this J1, J2 in 2D.
So at the end of your talk, you showed some curve of correlation along correlation versus distance, right?
Yes.
So you said some of them are power law decaying, and that's some like CDC alpha.
Here.
So so see, power law should be long range order, right?
No, this you mean this set of results, right?
Right.
Yeah, this is for suppose here there is no Hamiltonian. Basically, you suppose you can write the RVB wave function.
Mm-hmm.
Okay, in some language you can write this, and if you just calculate the corresponding correlation function, what you found is this. So since this is a gap system, the spin-spin correlation function should decay exponentially. That's okay. But the dimer one, which is related to singlet excitations for the square lattice, and if you include only short singlets in your wave function, what they found is an exponential algebraically.
So you didn't calculate this, just
No. Yeah, these are results from those guys here. What caught my attention was those results here, which looks like the one that I found. If you now increase the size of your singlets, or if you go to frustrate lattices, then both correlation functions decay exponentially.
it would be short range correlation.
Yeah, yes.
Now I got it. Thank you.
Okay.
Do we have any other questions? So let's thank the speaker again. Thank you very much, Ricardo. I'm going to be sending you an email asking for the slides so we can add the slides to the YouTube site.